In this presentation, we address berth allocation in tidal-dependent ports, where feasibility is governed by natural tidal cycles. In these environments, a berth plan is not just about matching vessels to spaces, it is also about matching vessel movements to time windows when the water is deep enough. This makes the decision space highly constrained. A schedule that looks good in a standard berth allocation model can become impossible once tidal depth and navigation timing are included. The goal is to allocate arriving vessels to berths when access is constrained by tidal windows. Unlike static berth allocation, feasibility depends on recurring tidal cycles that open and close navigation opportunities. Operationally, you must coordinate arrival times, berth depth profiles, tugboat support, and handling operations. If any of these pieces are misaligned, vessels wait until the next tide and costs escalate quickly. The scenario is the port of Hamburg on the Elbe River. The tidal range reaches up to 3.7 meters, which creates large changes in available depth over the day. The tide cycle repeats every 12 hours and 25 minutes. That periodicity becomes a planning rhythm. Schedules must be built around when deep draft vessels can safely transit and berth. Deep draft vessels can only navigate during limited tidal windows. In the example, the vessel MSC Allegra has a 14.2-meter draft and requests allocation at a major terminal. Its tidal window extends from 2 hours before high tide to 1 hour after, giving only a 3-hour opportunity in each cycle. Because that window occurs roughly every 12.4 hours, missing it forces a long wait. If a vessel misses its tidal window, it must wait for the next tidal cycle. This creates waiting costs and may also create knock-on disruptions, because berth and crane plans have to be reworked. Demurrage can exceed $50,000 per day, so even a half-day delay is financially significant. The operational impact also hits tugboat schedules, pilot coordination, and berth utilization. We will solve the problem with 5 tiers in this deck. Tier 1 provides a mathematical formulation that couples berth assignment with tidal window selection. Tier 2 uses hill climbing with random restarts. Tier 3 uses Cuckoo search with levy flights to explore the solution space globally. Tier 5 introduces an integrated digital twin. Tier 7 adds a human and artificial intelligence partnership for implementability. Tier 1 defines a model that couples berth assignment with tidal window selection. The key decisions are which berth a vessel uses, when service starts, and which tidal window is chosen. This tier is valuable because it makes feasibility explicit. When tides matter, the set of feasible start times is not continuous. It is restricted to windows that depend on both vessel draft and berth depth over time. This slide defines the sets of vessels and berth positions, plus the planning horizon. Operationally, these sets define the planning scope. The horizon must be long enough to cover at least 1 or 2 tidal cycles. Otherwise, you cannot represent the consequence of missing a window. This slide defines the set of tidal windows for each vessel. Each vessel has 1 or more windows, and each window is an interval with a start and end time. Operationally, this captures the navigation reality. Deep draft vessels are only feasible when depth and channel conditions allow safe passage and berthing. This slide defines the key vessel and berth inputs. For each vessel, the model includes earliest arrival time, required draft depth, processing time, and a demurrage cost rate. For each berth position, the model includes berth length and a time-dependent depth function. This depth function is what makes the problem tidal. It changes by time and can differ across berth locations. The model uses a binary berth assignment variable that indicates whether a vessel is assigned to a berth position. It uses a continuous start time for service. It also uses a binary tidal window selection variable, indicating which window the vessel uses for feasible access. The objective minimizes total weighted completion time, combining demurrage-weighted delay and penalties for choosing suboptimal tidal windows. Operationally, this objective reflects that delay has real financial impact, and not all feasible windows are equally desirable. Choosing a later window can reduce interference but increases weighting. This slide summarizes the full constraint set. Each vessel must be assigned to exactly 1 berth and exactly 1 tidal window. Service must start after the earliest arrival. The start time must be within the selected tidal window and must finish by the window's end. Depth at the assigned berth must be sufficient for the vessel's draft. Finally, vessels that share the same berth cannot overlap in service. The assignment constraint enforces that each vessel chooses exactly one berth. Operationally, this guarantees a complete plan and avoids duplicated service. It also prevents leaving a vessel unassigned, which would be equivalent to planning failure. This constraint enforces that each vessel selects exactly one tidal window. Operationally, this turns a vague feasibility idea into a discrete choice that the optimization can reason about. Which specific window will be used for safe access? This constraint requires the service start time to be at or after the earliest arrival. Operationally, this prevents scheduling a vessel before it is present and ready. It also emphasizes that early arrival uncertainty matters. When arrival times shift, feasibility against windows can change. This constraint ensures that service completion occurs by the end of the selected tidal window. A large constant is used to activate the deadline only for the selected window. Operationally, this models a hard cutoff. If the vessel cannot complete the critical part of the operation within the window, it becomes unsafe or impossible to proceed. This constraint ensures that service cannot start before the selected window begins, again activated through a large constant logic. Operationally, it enforces that the schedule respects the opening of the window, not just its closing. Starting too early is unsafe because depth is insufficient. This constraint links berth assignment to time-dependent depth. Depth at the chosen berth at the chosen start time must be at least the required draft. Operationally, it captures a major reason tidal planning is hard. Feasibility depends on both where you berth and when you berth. This slide summarizes the non-overlap requirement. If two vessels share a berth, their service intervals cannot overlap. Operationally, this is the berth as a scarce resource. Even if tidal windows are feasible, the berth cannot physically serve two vessels simultaneously. This figure visualizes vessel scheduling inside feasible tidal periods. Use it to verify feasibility at a glance. The schedule should place each vessel's service start within a valid window and should avoid overlaps that would block the berth. In the example, 3 vessels are scheduled over a 24-hour period. Vessel A has a 12-meter draft, 4 hours of processing, and arrives at 6 in the morning. Vessel B has a 14-meter draft, 6 hours of processing, and arrives at 8 in the morning. Vessel C has an 11-meter draft, 3 hours of processing, and arrives at 2 in the afternoon. High tides at 7:30 and 2000 provide 3-hour windows. The schedule starts Vessel A at 700 and completes at 1100. It starts Vessel B at 1900 and completes at 1 in the morning the next day. It starts Vessel C at 2030 and completes at 2330. The reported total weighted completion time is 47.5 hours with 0 tidal violations. Tier 2 uses hill climbing to improve a schedule via local moves, but it adds random restarts to avoid getting stuck in a poor local optimum. The neighborhood moves include swapping vessel assignments, shifting start times within feasible windows, and migrating a vessel to a different tidal window. This is a practical way to explore feasible corridors without solving a full exact model. This slide provides a high-level view of why the method's cost grows. Hill climbing with restart scales with how many restarts you try, how many neighboring moves you evaluate, and how expensive feasibility checks are. Operationally, feasibility checks dominate. Each neighbor must be validated against tidal window constraints, depth constraints, and non-overlap constraints. This figure illustrates the search landscape with both feasible and infeasible regions. The important operational insight is that many schedules are infeasible. A good heuristic must quickly reject infeasible neighbors and focus compute on feasible improvements. The trace starts from a random solution totaling 51.5 hours and is infeasible due to tidal violations. After 5 iterations, the method finds a feasible schedule with total 39.5 hours. This is described as a 16% improvement over the mathematical solution, and the improvement comes from aligning each vessel's start time with the correct tidal windows. This code section defines the hill climbing with restart loop, tracking the best solution across restarts. Operationally, the restart mechanism is a hedge against local optima. If one search path stalls, a new random initial schedule can move the search into a different feasible corridor. This section generates neighbors by swapping vessel assignments and shifting start times by small deltas. Operationally, these moves correspond to realistic dispatch adjustments, trading berths between vessels and nudging arrival alignment to fit within tidal windows. This section outlines objective evaluation as a demurrage-weighted delay cost. Operationally, the key is that feasibility checking is external to evaluation. You first validate tidal and overlap constraints, then score the cost of the feasible neighbor. Tier 3 uses Cuckoo search, where each nest represents a candidate schedule, and new schedules are generated by levy flight-style random walks. A discovery probability determines how often poor nests are abandoned and replaced with new random solutions. This mechanism keeps exploration active while still preserving the best schedules. This slide presents the levy flight distribution used to generate step sizes. Operationally, levy flights enable occasional large jumps. That helps the algorithm escape local basins by proposing substantially different berth or timing configurations. This figure shows the core mechanics. Levy flights generate candidate solutions, nests compete by objective value, and worse nests are replaced. Operationally, the method balances diversification and intensification. It explores broadly while also pushing the population toward better schedules. The initial population includes 5 nests with objectives roughly between 45 and 55 hours, and 1 nest is infeasible. After 100 iterations, the best objective is 37.8 hours, reported as 5% better than hill climbing. A subtle optimization is starting vessel C 15 minutes earlier within its window, which reduces waiting while remaining feasible. Convergence is reported at iteration 87. This code section initializes a population of nests, evaluates fitness, and sets parameters like discovery probability and the levy flight parameter. Operationally, these parameters determine how exploratory the search is. Higher discovery leads to more resets, while the levy parameter shapes how often large jumps occur. This section generates new nests using levy flights and replaces worse nests when an improvement is found. Operationally, replacement is a competitive selection mechanism. It ensures that the population gradually shifts toward lower-cost schedules without requiring gradient information. This section abandons the worst nests and regenerates them randomly based on the discovery probability. Operationally, abandonment prevents stagnation. It injects diversity when the population becomes too similar and stops improving. This section tracks convergence and can stop early if improvement becomes negligible. Operationally, early stopping is a runtime control. In a port setting, you want improvements, but you also need decisions fast enough to act on them. Tier 5 builds a system of systems digital twin that integrates real-time tides, AIS vessel tracking, weather, and resource availability. The digital twin runs continuous optimization and scenario simulation. The idea is to shift from one-time planning to ongoing adaptation as predictions and conditions change. This figure shows the architecture that combines real-time tidal data with integrated optimization. Operationally, the core requirement is timely synchronization. If the twin lags too far behind reality, it cannot produce reliable schedules for the next tidal window. In a 30-day evaluation at Port of Hamburg, the system processes 247 vessel arrivals, 8,760 hourly tidal sensor readings, 1,440 hourly weather updates, and 720 resource status updates. Reported improvements include an 18% reduction in average waiting time, a 12% improvement in berth utilization, a 23% reduction in tidal window violations, and a 15% decrease in tugboat idle time. The system also prepares for storms with 6-hour delays, tugboat maintenance, arrival clustering, and spring tide extremes. This code section defines the tidal berth digital twin and its core subsystems: tidal prediction, vessel tracking, resource management, optimization, simulation, and analytics. Operationally, subsystem separation matters. It lets the twin update tidal predictions and vessel positions independently while still feeding a unified optimization scenario. This section describes a continuous optimization loop with a 5-minute cycle. Operationally, the 5-minute cadence is a compromise. Fast enough to react to changes, but slow enough to run optimization, validate schedules, and publish updates to operations. This section describes predictive scenario generation for weather impact, vessel delay, equipment failure, and peak demand. Operationally, scenario simulation supports proactive planning. If the system detects risk of missing a window, it can propose alternatives before the window is lost. This section shows how tidal predictions are updated using sensor readings and weather inputs, and how updated tidal windows are propagated to each berth. Operationally, this is the bridge between physics and scheduling. Better tidal predictions directly improve feasibility and reduce window violations. Tier 7 combines AI optimization with human operational insight. The system provides explainable recommendations and supports collaborative refinement. Operationally, this tier recognizes that not all constraints are formal. Captain preferences, local maneuvering realities, and stakeholder relationships can change what is practically feasible. This slide focuses on explainable AI plus human-in-the-loop decisions. Operationally, the explanation module must translate optimization trade-offs into clear operational language, so port managers can accept, modify, or explore alternatives quickly. In the scenario, 5 large vessels arrive within 4 hours during spring tide conditions, with 1 tugboat out of service. The AI produces an initial recommendation with a confidence score of 82% and delays 2 vessels to the next window. A human manager adds an operational preference. The captain of MSC Mediterranean prefers berth 1 due to easier maneuvering with reduced tugboat support. After re-optimization, the collaborative solution accommodates all 5 vessels in the current window. Reported outcomes include a 12% improvement in tugboat efficiency, 0 captain complaints, and 95% schedule adherence. The trust score improves from 82% to 91% after the system learns this preference. This code section defines a collaborative optimization session where the AI generates recommendations and the human interface responds. Operationally, this creates a structured workflow. Instead of informal overrides, the system records decisions and can learn from repeated patterns. This section outlines explanation generation and confidence breakdown components. Operationally, confidence breakdown is important because uncertainty is not uniform. Tidal prediction accuracy, vessel arrival reliability, resource certainty, and weather confidence all contribute differently to risk. This section shows human-led problem-solving when no AI recommendation is acceptable. Operationally, this prevents decision paralysis. It acknowledges that in rare situations, humans must lead while still using AI to solve decomposed subproblems.